And welcome back to Simple Circuits 101. This is my latest project called My Little Robot.
Oh, he's so cute!
As per usual, I'm using the blue tack and spit roast method of construction, placing the small discrete components in first. Secure the components with the obligatory blob of blue tack. Always clean the soldering iron tip before you begin any soldering work. Make a point of truing and aligning the components as you go along. This isn't just for aesthetic reasons. Having the components laid out in a uniform manner helps in fault finding later on in the build. Before the component legs become a small forest, trim them down a bit with the close cropping tool. This is the variable resistor. It experiences some mechanical stress during operation, so be mindful of this fact and ensure a good quality soldered joint. Pop in the deal socket, make sure it's the right way round. Blob of blue tack there, turn it over and then secure diagonally. Then address the other joints. The long lead of the capacitor denotes the positive connection. Secure one lead first, turn it over, straighten, and then secure the other lead. Place the switch with the black dot pointing towards the robot's head. As with other dual inline components, first address the diagonal pins, check for alignment, and then address the remaining pins. This is the transistor. Align that with the silkscreen image on the PCB and secure the centre pin first. Make sure this component's straight as it represents the robot's nose, and you don't want a robot with a wonky nose. These are the robot's eyes. The long leads indicate the positive connection. Notice here how I'm close cropping the component's leads and then resoldering to produce a domed aesthetic. I like to call this effect the solder dome. And here's a picture. This is the battery clip. Trim the ends back to about 1 inch and tin the ends. Pop the leads in, making a note of the polarity, secure with a bit of blue tack and solder in place. Now to place the sticky pad, but first let's clean the area with a bit of methylated spirits and a toothbrush. Now here's something I want to share with you. Earlier in the build I experimented with the value of one of the resistors, and this necessitated removing the original component using a solder sucker. Quite a tricky operation. Now back to the build and pop the sticky pad there. A bit fiddly. Place the battery backpack and push down firmly to secure. In goes the chip. Connect the battery. Using a bit of hot glue there to help support the wires. To make the eyes pulse faster, adjust the variable resistor anti-clockwise. And to make the eyes pulse slower, adjust the variable resistor clockwise. final part of the construction is to put the robot's boots on, like so.
Ooh, he's mesmerizing me.
This is the circuit diagram for the My Little Robot project. Let's take a closer look at what's going on here. Let me give you a quick walk around of the circuit. First you have the double pole, double throw latching switch. Notice how I've used both sides of the switch for redundancy purposes. Moving on, we have the reverse polarity protection diode. Just in case someone puts the battery in the wrong way around, that will protect the rest of the circuit from coming to harm. Here we have the BC547 transistor. Nothing particularly special about this one, it's what I would term as vanilla. And that supplies the two red 5mm LEDs. This arrangement of resistors is called a voltage divider. It provides a voltage reference point to the op-amp of half the supply voltage, in this case a nominal 4.5 volts. Let's have a look what's going on inside the op-amp. Here's a cutaway view of the LM358 OpAmp. This DIL package contains two op-amps. Op-amp is an abbreviation of operational amplifier. They were used extensively in analog computers back in the day to perform mathematic operations. They're still used today in many varied applications, including automation, instrumentation, audio and video devices. This diagram shows the cutaway view of the op-amp in circuit. Let me give you a quick, rough and ready explanation of what's going on here. Op-amp A is configured as a ramp generator, and op-amp B is configured as a non-inverting Schmitt trigger. Op-amps work by attempting to equalize any voltage difference between their inputs by compensating with their outputs. Resistors R1 and R2 form a voltage divider network, which is half that of the supply voltage. In this case, approximately 4.5 volts. This is the op-amp's reference voltage. So, arbitrarily beginning with capacitor C1 in a discharge state, op-amp A detects that the voltage at pin 2 is lower than that of pin 3. It attempts to compensate for the imbalance by increasing the output voltage at pin 1. This produces a steady, linear voltage rise at pin 1 as the capacitor C1 charges. This voltage is presented to the base of transistor Q1. As the voltage rises, the transistor starts to turn on, allowing current to flow to the LEDs, which then begin to light up. When the voltage at pin 5, adjustable by VR1, equals the value at pin 6, op-amp B triggers and presents a voltage at pin 2 of op-amp A, which is higher than that of the reference voltage seen at pin 3. The output of op-amp A on pin 1 no longer has to compensate for the imbalance, and capacitor C1 begins to discharge. As the voltage falls, transistor Q1 begins to turn off and the LEDs dim. When the voltage at pin 2 is again lower than that of pin 3, the output of op-amp A attempts to compensate for the imbalance again, and as a consequence charges capacitor C1, and so the cycle repeats. Nice. This is the triangle waveform seen at the emitter of transistor Q1. And this is the on-screen display of the various values. This is the waveform present at the anodes of the LEDs. Observe the rise and fall of the waveform and the corresponding effect on the intensity of the LEDs. Here's a few still images of My Little Robot in all its glory.
Oh my word, he's so cute. I must have one.
Well, I hope you enjoyed this project. If you did, please like and subscribe.
I want to be your friend. Always.
My Little Robot is not self-aware and is not an associate of Cyberdan Systems. Terms and conditions apply.